The solar system feels familiar because it is home. 8 planets orbit a stable star. Moons circle those planets in predictable paths. The sun rises and sets with reliable rhythm. From Earth's surface, the cosmos appears orderly, distant, and calm. Yet, when examined more closely, that sense of safety begins to soften. The solar system contains environments so hostile that human survival would be measured not in days or hours, but in minutes or seconds. Temperatures that melt metal, radiation that tears through matter, storms larger than continents that have raged for centuries, gravitational forces that would crush a human body instantly. Welcome to Sleep Knowledge. If you find comfort in exploring the quieter corners of cosmic violence, settle in and let these disturbing facts about our solar system unfold slowly. And if you feel moved to, share where you are drifting off tonight. It is always warming to know how far these quiet thoughts travel. This is not sensationalism. These are measurements taken by spacecraft, designed to withstand conditions no human could survive. Observations recorded by instruments that traveled millions of miles to document what exists beyond Earth's protective bubble. The solar system's violence is not theoretical. It is real, measured, and surprisingly close to home. What makes these facts unsettling is not their distance, but their proximity. Venus orbits just 26 million miles from Earth at its closest approach. Jupiter's radiation belts extend millions of miles into space, influencing regions far from the planet itself. The Sun, which makes life possible, also releases energy bursts, capable of disrupting every electronic system on Earth. Understanding this violence does not make the solar system less reliable. The patterns remain stable. The orbits continue. The forces that seem terrifying to human biology operate according to consistent physical principles. A planet with crushing atmospheric pressure maintains that pressure predictably. A radiation belt accelerates particles according to the same rules it has followed for billions of years. There is something oddly calming in that stability. The solar system's hostility is not random or chaotic. It is structured, repeatable, and thoroughly documented. What seems frightening from a human perspective represents the normal operation of physical processes that have shaped these worlds since their formation. Settle in and let this exploration of our solar system's disturbing realities unfold gently. Venus appears beautiful from Earth. The morning star, the evening star, a brilliant point of light that has guided travelers and inspired poetry for thousands of years. Its brightness comes from thick clouds that reflect most sunlight back into space, making Venus the most luminous object in Earth's night sky after the Moon. Those same clouds conceal conditions so extreme that Soviet spacecraft designed to land on the surface functioned for only minutes before succumbing to the environment. Not hours, minutes. And in those brief operational windows, the data they transmitted revealed a world that redefined what planetary scientists considered possible. The surface temperature of Venus reaches approximately 737 Kelvin, which translates to 464 degrees Celsius, or 867 degrees Fahrenheit. This is hot enough to melt lead, which liquefies at 621 degrees Fahrenheit. Hot enough to melt zinc. Hot enough that traditional electronics cease functioning within seconds of exposure. What makes this temperature particularly unsettling is its consistency. On Earth, temperature varies dramatically between day and night, between equator and poles, between seasons. Venus's surface temperature remains virtually constant across the entire planet. The night side is as hot as the day side. The poles are as hot as the equator. The thick atmosphere redistributes heat so efficiently that temperature variation across the entire surface amounts to only a few degrees. This is not the closest planet to the Sun. Mercury orbits nearer to the Sun than Venus, yet Mercury's surface temperature, while extreme, reaches only about 800 degrees Fahrenheit on the day side and plunges to minus 290 degrees Fahrenheit at night. Venus, farther from the Sun, maintains a surface temperature higher than Mercury's peak temperature, constantly, everywhere, without variation. The mechanism behind this is well understood. Venus's atmosphere consists of 96.5% carbon dioxide, creating the most powerful greenhouse effect in the solar system. Sunlight penetrates the cloud layers and warms the surface. The surface radiates that energy back as infrared radiation. But the dense carbon dioxide atmosphere traps that infrared energy, preventing it from escaping into space. The trapped heat accumulates, driving surface temperatures to extraordinary levels. This greenhouse effect demonstrates a process that operates on Earth as well, though at vastly different scales. The same physics that keeps Venus at 867 degrees Fahrenheit operates in Earth's atmosphere to maintain temperatures suitable for liquid water. The difference lies in degree, not kind. What makes Venus's greenhouse effect remarkable is not that it violates physical principles, but that it follows those principles to their logical extreme. The atmosphere itself presents additional hazards. Surface pressure on Venus measures approximately 92 times Earth's atmospheric pressure at sea level. This is equivalent to the pressure experienced at a depth of about 3,000 feet underwater in Earth's oceans. At that depth, human lungs would collapse, the rib cage would compress, and consciousness would be lost within seconds. On Venus, this crushing pressure exists not deep underground or underwater. Simply standing on Venus's surface, if the heat could somehow be endured, would mean experiencing pressure sufficient to compress the human body with a force of more than 1 ton per square inch. The Soviet Venera landers, built like deep-sea submarines with thick metal hulls and pressure-resistant construction, survived this environment only briefly. The clouds themselves add another layer of hostility. Venus's clouds consist primarily of sulfuric acid. These are not wispy water vapor clouds like those on Earth, but droplets of concentrated acid suspended in the atmosphere at altitudes of 45 to 70 kilometers above the surface. The acid is corrosive enough to burn through many materials, adding chemical hazard to the already formidable thermal and pressure challenges. Yet spacecraft have survived long enough to transmit data. The Venera missions, launched by the Soviet Union between 1961 and 1984, provided humanity's first direct measurements of Venus's surface conditions. Venera 7, in 1970, became the first spacecraft to transmit data from another planet's surface, functioning for 23 minutes before succumbing to the heat. Venera 13, in 1982, transmitted the first color images from Venus's surface and survived for 127 minutes, far exceeding its design specifications. These achievements required extraordinary engineering. The landers were pre-cooled before descent. Their electronics were insulated inside pressure-resistant spheres. Their external components were built from materials capable of withstanding high temperatures and corrosive environments. Even with these precautions, the environment eventually overwhelmed each spacecraft. NASA's Mariner and Pioneer missions confirmed these measurements from orbit, using instruments to probe the atmosphere and surface without landing. The data consistently showed the same extreme conditions across multiple missions spanning decades. Venus's hostility is not an anomaly or a measurement error. It is the planet's normal state, verified repeatedly by independent spacecraft from different space programs. What this means for human exploration remains uncertain. Venus's upper atmosphere, at altitudes around 50 kilometers, presents more Earth-like conditions. Temperatures there range from 30 to 70 degrees Celsius, and pressure approximates Earth's surface pressure. Some proposals for Venus exploration envision floating research stations suspended in this habitable zone, far above the deadly surface. But the surface itself, with its combination of crushing pressure, melting temperatures, and corrosive atmosphere, remains one of the most hostile environments in the solar system. The fact that it exists on the planet closest to Earth, visible to the naked eye, on any clear evening, adds an unsettling proximity to this cosmic violence. Jupiter dominates the outer solar system. More massive than all other planets combined, it generates a magnetic field vastly stronger than Earth's. This field traps charged particles, accelerating them to extraordinary energies and creating radiation belts that represent some of the most hazardous conditions known to space exploration. Earth possesses radiation belts discovered in 1958 by Explorer 1 and named after physicist James Van Allen. These belts contain energetic particles trapped by Earth's magnetic field, and spacecraft traveling through them require radiation-hardened components to function reliably. But Earth's radiation belts, while significant, pale in comparison to Jupiter's. Jupiter's radiation environment received its first direct measurement when Pioneer 10 passed within 2.9 Jupiter radii of the planet's center in December 1973. The spacecraft's instruments recorded radiation levels 10 times higher than engineers had anticipated. Pioneer 10 received an integrated dose of 200,000 rads from electrons and 56,000 rads from protons during its flyby. To understand this measurement, consider that a whole-body dose of 500 rads is lethal to humans. Pioneer 10, traveling through Jupiter's radiation belts for just a few hours, received radiation exposure equivalent to 400 times a lethal human dose from electrons alone. The spacecraft survived this encounter only because Jupiter's magnetosphere had shifted slightly at the moment of closest approach, moving the most intense radiation zones temporarily away from the spacecraft's trajectory. Later missions confirmed and refined these measurements. NASA's Galileo spacecraft, which orbited Jupiter from 1995 to 2003, carried radiation-hardened electronics and shielding specifically designed for Jupiter's environment. Even with these precautions, the radiation gradually degraded the spacecraft's components. By mission's end, Galileo had received a cumulative radiation dose equivalent to approximately 25 times a lethal human dose. The European Space Agency's Jupiter Icy Moons Explorer mission, JUICE, faces similar challenges. Mission planners calculated that less than 4 years at Jupiter will expose the spacecraft to radiation equivalent to what a telecommunications satellite receives during 20 years in geostationary orbit around Earth. JUICE's most sensitive electronics are housed in lead-lined vaults within the spacecraft, providing shielding that adds significant mass but is essential for mission survival. Europa, one of Jupiter's large Galilean moons, and a prime target for astrobiology research due to its subsurface ocean, orbits within Jupiter's radiation belts. Any human astronaut standing on Europa's surface unprotected would receive a lethal radiation dose within hours, not days. The moon's position makes it one of the most radiation-intense destinations in the solar system. The source of Jupiter's extreme radiation environment is well understood. The planet's rapid rotation, completing one full turn every 10 hours, combines with its strong magnetic field to create a magnetic environment extending millions of kilometers into space. Charged particles, primarily originating from volcanic gases emitted by the moon Io, are trapped by this magnetic field and accelerated to near light speed. These high-energy electrons spiral along magnetic field lines, creating intense belts of radiation, similar in structure but far more energetic than Earth's Van Allen belts. The particles carry enough energy to penetrate spacecraft shielding, damage sensitive electronics, and disrupt computer memory. They generate synchrotron radiation, a form of electromagnetic emission that astronomers have detected from Earth using radio telescopes. The radiation poses not just a hazard to spacecraft electronics, but a fundamental challenge to human exploration. Future missions carrying humans to Jupiter's moons would need to minimize time spent in the radiation belts, use trajectories that avoid the most intense regions, and employ shielding far beyond what current technology provides. The physics of radiation protection sets hard limits on what is possible. Europa's surface receives approximately 5.4 sieverts of radiation per day. For comparison, radiation workers on Earth are limited to 50 millisieverts per year, and the lethal dose for humans is approximately 5 sieverts in a short period. Europa receives a lethal human dose every single day, continuously, as a normal condition of its orbital position. This does not make Europa uninteresting, quite the opposite. The same radiation that makes surface exploration hazardous also creates chemical compounds that could potentially support life in the ocean beneath Europa's ice shell. Radiation breaks apart water molecules into hydrogen and oxygen, creates oxidants that could provide energy for biological processes, and drives chemistry that might support an alien biosphere. But it does make Europa's surface one of the most hostile destinations in the solar system from a human survival perspective. The radiation is not a temporary phenomenon or a periodic hazard. It is a permanent feature of the environment, sustained by Jupiter's magnetic field and Io's volcanic activity, both of which show no sign of diminishing. NASA's Juno mission, currently orbiting Jupiter, employs a unique trajectory that repeatedly passes over Jupiter's poles while minimizing time in the most intense radiation regions. Even so, Juno's electronics are expected to accumulate radiation equivalent to about 10 million dental X-rays over the course of its mission. The spacecraft was designed with this in mind, using radiation-tolerant components and triple redundant systems to maintain functionality despite gradual degradation. The radiation belts extend far beyond Jupiter itself. At their most extensive, Jupiter's magnetosphere measures approximately 20 million kilometers across, making it the largest structure in the solar system besides the Sun's heliosphere. Within this vast region, radiation intensity varies depending on distance from Jupiter and proximity to the planet's moons, which sweep up particles along their orbital paths, creating relatively protected zones. Understanding Jupiter's radiation environment required decades of spacecraft missions, mathematical modeling, and theoretical work. The JOSY model, developed by ESA's Space Environment and Effects section, provides mission planners with detailed predictions of radiation exposure for different trajectories and mission durations. This model incorporates data from Pioneer, Voyager, Galileo, and other missions to create a comprehensive picture of Jupiter's radiation environment. What emerges from this accumulated knowledge is a clear picture. Jupiter's radiation belts represent one of the most extreme environments in the solar system, far more intense than anything found in near-Earth space, and a fundamental challenge to spacecraft design and human exploration. The radiation is real, measured, and thoroughly documented. It operates according to well-understood physical principles, and it makes Jupiter's neighborhood one of the most hazardous destinations in the solar system. Io, the innermost of Jupiter's large Galilean moons, ranks as the most volcanically active body in the entire solar system. Its surface features hundreds of active volcanoes, some erupting continuously, others intermittently, collectively resurfacing the moon so rapidly that no impact craters have survived from the early solar system. Every impact crater that formed on Io's surface billions of years ago has been buried beneath layer after layer of volcanic material. Voyager 1 discovered Io's volcanic activity in 1979, when navigation engineer Linda Morabito noticed a plume extending from the moon's limb in an image. This discovery marked the first observation of active volcanism beyond Earth. Subsequent observations by Voyager 2, Galileo, and other spacecraft documented the full extent of Io's volcanic activity, revealing a world constantly resurfacing itself through volcanic processes more vigorous than Earth's geological activity. Io's volcanoes are not gentle features. Some volcanic plumes reach altitudes of 300 kilometers above the surface, carrying sulfur compounds and other volcanic gases into Io's tenuous atmosphere before falling back to the surface. These plumes represent some of the most powerful volcanic eruptions observed in the solar system, ejecting material at velocities that would place it in orbit around Earth. The energy driving this volcanic activity comes not from radioactive decay, as on Earth, but from tidal heating. Io orbits Jupiter in a path that is slightly elliptical due to gravitational interactions with Europa and Ganymede. As Io moves closer to and farther from Jupiter during each orbit, Jupiter's immense gravitational field creates tidal forces that flex Io's interior, generating friction and heat. This tidal heating amounts to approximately 100 trillion watts of power, roughly 200 times greater than all volcanic and tectonic activity on Earth. The heating is so intense that Io's interior remains largely molten beneath a thin, solid crust. Magma chambers exist close to the surface, feeding volcanic eruptions that coat Io's surface with sulfur compounds, silicate lavas, and other volcanic materials. Io's surface appears colorful in spacecraft images, with yellows, oranges, whites, and dark regions creating a patchwork appearance. These colors result from various sulfur compounds and their oxidation states deposited by volcanic activity. Sulfur dioxide frost covers many regions, creating white deposits. Elemental sulfur creates yellow and orange tones. Silicate rocks produce darker grays and browns. Temperatures on Io's surface vary dramatically. In non-volcanic regions, temperatures drop to approximately minus 163 degrees Celsius. But active lava flows reach temperatures exceeding 1,500 degrees Celsius, far hotter than typical basaltic lavas on Earth. Some of Io's lavas may reach temperatures as high as 1,600 degrees Celsius, comparable to the hottest lavas Earth produced billions of years ago, when the planet's interior was significantly hotter than today. Specific volcanoes on Io have been observed and studied across multiple spacecraft missions. Patera, the most powerful volcano in the solar system, contains a lava lake approximately 200 kilometers in diameter. The lava lake periodically overturns as cooled crust sinks and fresh magma rises, creating brightness variations detectable from Earth-based telescopes. Patera alone emits more heat than all of Earth's volcanoes combined. Pele, another prominent volcano, produces reddish-orange plumes that deposit sulfur compounds in a ring approximately 1,400 kilometers in diameter around the eruption site. The plume extends more than 300 kilometers above Io's surface, making it one of the highest volcanic plumes in the solar system. The color and composition of Pele's deposits indicate sulfur-rich lavas erupting at high temperatures. Prometheus, nicknamed Old Faithful for its persistent activity, has been observed erupting continuously since Voyager 1 first documented it in 1979. The plume extends approximately 100 kilometers above the surface and has maintained its activity for at least 40 years, demonstrating the sustained nature of Io's volcanic processes. Io's volcanic activity creates a direct connection to Jupiter's radiation belts. The volcanoes eject approximately 1 ton of sulfur dioxide and other gases into space every second. These gases become ionized by solar ultraviolet radiation and Jupiter's magnetosphere, creating a torus of charged particles along Io's orbit. Jupiter's magnetic field sweeps up these particles and accelerates them, contributing to the radiation belts discussed earlier. This plasma torus can be observed from Earth using specialized telescopes. It glows faintly due to excitation of ions by electron collisions, creating emissions at specific wavelengths characteristic of ionized sulfur and oxygen. The torus represents material flowing from Io's volcanoes into Jupiter's magnetosphere, demonstrating the direct coupling between geological activity on a moon and the space environment around a planet. For future exploration, Io presents multiple challenges. The intense volcanic activity makes surface temperatures variable and potentially hazardous. The thin atmosphere provides no protection from radiation. Io's position within Jupiter's radiation belts means that surface radiation levels are extremely high, and the constant resurfacing means that landing sites could be covered by fresh volcanic deposits within years or decades. Yet Io remains scientifically fascinating precisely because of its extreme volcanic activity. The Moon provides a natural laboratory for studying tidal heating, magma generation, and volcanic processes under conditions different from Earth. Understanding Io's volcanism informs models of tidal heating on other moons, including Europa and Enceladus, where similar processes may operate beneath ice shells. Io demonstrates that gravitational interactions in the solar system can generate geological activity, rivaling or exceeding activity driven by internal radioactive decay. The Moon's interior remains molten, not because it contains more radioactive elements than other moons, but because Jupiter's gravity continuously deforms it, generating heat through friction. This process has sustained Io's volcanism across billions of years. Europa, another of Jupiter's Galilean moons, presents a starkly different environment from volcanic Io. Europa's surface consists of water ice, cracked and fractured into complex patterns, suggesting geological activity beneath. But unlike Io's obvious surface volcanism, Europa's activity remains hidden beneath an ice shell kilometers thick, where a vast ocean of liquid water may harbor conditions suitable for life. Evidence for Europa's subsurface ocean comes from multiple sources. The Galileo spacecraft measured Europa's magnetic field and detected variations consistent with a conductive fluid beneath the surface. Salt water conducts electricity. Ice does not. The magnetic field measurements strongly suggest that a salty ocean exists beneath Europa's ice shell, extending perhaps 100 kilometers deep. Europa's surface features also support this interpretation. The ice shell shows evidence of tectonic activity, with cracks, ridges, and regions where surface ice appears to have broken apart and refrozen in chaotic patterns. These features suggest that the ice shell floats on liquid water, responding to tidal stresses similar to those that heat Io's interior, though with less extreme effects. The estimated depth of Europa's ocean exceeds Earth's oceans. Despite Europa's smaller size, models suggest Europa may contain twice as much liquid water as all of Earth's oceans combined, making it one of the most water-rich worlds in the solar system. This water remains liquid due to tidal heating from Jupiter and possibly radioactive heating from Europa's rocky interior. The ocean's potential habitability depends on several factors. Liquid water is necessary but not sufficient for life. The ocean would also need energy sources to support biological processes, chemical nutrients to build complex molecules, and sufficient time for life to develop. Europa may provide all these conditions. Radiation from Jupiter's magnetosphere strikes Europa's surface, breaking apart water molecules and creating oxidants like hydrogen peroxide. These oxidants could be transported to the subsurface ocean through cracks in the ice, or during periodic resurfacing events. In the ocean, the oxidants could react with reduced compounds from Europa's rocky seafloor, providing chemical energy that hypothetical organisms could exploit. Hydrothermal vents, similar to those found on Earth's ocean floors, may exist on Europa's seafloor. These vents would provide localized heat, chemical nutrients, and energy sources similar to the environments where some of Earth's most unusual ecosystems thrive. On Earth, entire biological communities exist around deep-sea hydrothermal vents, independent of sunlight, sustained by chemical energy from the vents. Europa's surface temperature averages approximately -160 degrees Celsius, cold enough that the ice shell remains solid despite the liquid ocean beneath. The ice shell's estimated thickness ranges from a few kilometers in some regions to perhaps 30 kilometers in others, with thinner regions showing more evidence of recent geological activity. The combination of a subsurface ocean, potential energy sources, and chemical nutrients makes Europa one of the highest priority targets for astrobiology research. NASA's Europa Clipper mission, scheduled to launch in 2024, will conduct detailed reconnaissance of Europa through multiple flybys, measuring ice shell thickness, sampling any plumes of water vapor erupting from the surface, and assessing the habitability of Europa's ocean without landing on the surface. The challenges of exploring Europa's subsurface ocean remain formidable. Drilling through kilometers of ice requires technology not yet developed. The high radiation environment surrounding Europa damages electronics and shortens mission lifetimes. The need to avoid contaminating Europa with Earth microorganisms requires extraordinary sterilization procedures. But the potential scientific return justifies these challenges. If life exists in Europa's ocean, it would represent the second independent origin of life discovered in the solar system, profoundly altering understanding of life's prevalence in the universe. If life does not exist despite favorable conditions, that finding would inform models of how life arises and what factors limit its development. Either outcome would provide crucial data for astrobiology and the search for life beyond Earth. Saturn, the sixth planet from the Sun, presents multiple mysteries beyond its famous rings. But before exploring the hexagonal storm at Saturn's pole, attention turns to Titan, Saturn's largest moon and one of the most Earth-like yet profoundly alien worlds in the solar system. Titan stands unique among solar system moons for possessing a substantial atmosphere, thicker than Earth's and composed primarily of nitrogen with traces of methane and other hydrocarbons. Surface pressure on Titan measures approximately 1.5 times Earth's atmospheric pressure at sea level, making Titan the only moon with a surface pressure greater than Earth's. But Titan's atmosphere creates an environment utterly unlike Earth. Despite the similar pressure, temperatures at Titan's surface average -179 degrees Celsius, cold enough that water ice behaves like rock and methane exists in liquid form. This creates a hydrological cycle powered by methane rather than water, with methane rain, rivers, lakes, and seas distributed across Titan's surface. The Cassini-Huygens mission, which orbited Saturn from 2004 to 2017 and deployed the Huygens probe to Titan's surface in 2005, revealed the full extent of this methane cycle. Radar mapping detected numerous lakes and seas in Titan's polar regions, with the largest, Kraken Mare, covering approximately 400,000 square kilometers, larger than the Caspian Sea on Earth. These are not water bodies, but reservoirs of liquid methane and ethane, hydrocarbons that exist as gases at room temperature on Earth, but remain liquid in Titan's cold environment. The lakes show shorelines, depth variations, and evidence of seasonal changes in liquid levels, demonstrating that Titan possesses a complete hydrological system analogous to Earth's water cycle, but operating with entirely different chemistry. Methane rain falls from Titan's clouds, accumulating in rivers that flow toward the polar lakes. Cassini's radar observations documented several river systems, some extending hundreds of kilometers from highlands to lowland lake basins. The rivers appear darker in radar images than surrounding terrain, consistent with liquid carved channels filled with hydrocarbons. Titan's atmosphere frequently develops cloud systems that obscure the surface. Some clouds produce methane precipitation, with rainfall rates and droplet sizes estimated from atmospheric models and Huygens probe data. The rain falls slowly in Titan's low gravity and thick atmosphere, taking longer to reach the surface than rain on Earth, but carrying sufficient energy to erode surface materials and transport sediments. The surface itself consists of water ice bedrock overlain with organic deposits, creating a landscape of icy mountains, hydrocarbon dunes, and liquid-filled basins. The Huygens probe landed on what appeared to be a dried lakebed or riverbed, finding a surface consisting of ice pebbles cemented together with frozen methane and other organics. The consistency resembled wet sand or mud, demonstrating that Titan's surface materials behave differently from familiar rocky or icy materials. Wind patterns on Titan create dunes of organic materials near the equator. These dunes, detected by Cassini's radar, extend for hundreds of kilometers and reach heights of approximately 100 meters. They consist of fine particles, likely complex hydrocarbons, that have settled from the atmosphere and been organized by wind into linear dune fields oriented parallel to prevailing winds. The organic chemistry occurring in Titan's atmosphere represents a natural laboratory for prebiotic chemical processes. Sunlight and charged particles from Saturn's magnetosphere break apart nitrogen and methane molecules in the upper atmosphere, creating reactive fragments that recombine into more complex molecules. This process, continuing over billions of years, has produced a thick organic haze that gives Titan its characteristic orange color. Some of these organic molecules, including complex hydrocarbons and nitrogen-containing compounds called nitriles, eventually settle to Titan's surface, accumulating over time. Models suggest that Titan's surface may be covered with organic sediments meters or even tens of meters deep in some regions, representing accumulated chemical products from billions of years of atmospheric chemistry. What makes Titan particularly intriguing for astrobiology is the possibility of a subsurface water ocean beneath the ice shell. Like Europa, Titan shows evidence from gravity measurements and surface deformation of a liquid layer beneath the surface. This ocean would consist of water mixed with ammonia, remaining liquid at temperatures below water's freezing point due to ammonia's antifreeze properties. If Titan possesses both surface hydrocarbon lakes and a subsurface water ocean, it could harbor two distinct environments potentially suitable for life, each based on different solvents and chemical processes. Surface organisms, if they exist, would need to operate in liquid methane at extremely cold temperatures. Subsurface organisms would occupy a more familiar water-based environment, but one isolated from sunlight and requiring energy sources from Titan's interior, or chemical gradients between the ocean and the rocky core below. Current evidence does not confirm life on Titan. The environment presents significant challenges for biology. The extreme cold slows chemical reactions dramatically. The lack of abundant oxidants limits energy sources. The surface receives minimal sunlight, filtered through Titan's thick atmosphere. But Titan's chemical complexity and environmental diversity make it a compelling target for future exploration. NASA's Dragonfly mission, scheduled to launch in 2027, will send a nuclear-powered rotorcraft to explore Titan's surface, flying between sites of scientific interest and sampling surface materials to analyze their composition. The mission will search for complex organic molecules, assess habitability conditions, and investigate Titan's methane cycle in detail. This represents humanity's first attempt to systematically explore a world where lakes, rivers, and rain consist of hydrocarbons rather than water. Titan's methane cycle adds another dimension to the solar system's environmental diversity. Beyond the extremes of temperature, pressure, and radiation found on other worlds, Titan presents a world where familiar processes, rain, and rivers and lakes, operate with alien chemistry. The landscape appears superficially familiar, with lakes and rivers and coastlines, but the liquids are hydrocarbons, and the bedrock is water ice, and the rain falls from orange skies in an atmosphere too cold for liquid water, but perfectly suited for liquid methane. Saturn's North Pole contains a structure that has puzzled planetary scientists for decades. A jet stream roughly 20,000 miles in diameter, flowing at speeds exceeding 200 miles per hour, forms a nearly perfect hexagon, 6 straight sides, 6 sharp corners. A geometric precision that seems impossible in the chaotic environment of a gas giant's atmosphere. The hexagon was discovered in 1981, when astronomer David Godfrey analyzed data from the Voyager 1 and Voyager 2 flybys of Saturn. The images showed something unprecedented in planetary science. A weather pattern with a clear geometric structure, maintained stable for at least the duration between the two Voyager passes. Nothing like it has been observed on any other planet in the solar system. NASA's Cassini spacecraft, which orbited Saturn from 2004 to 2017, provided extensive observations of the hexagon over multiple Saturnian seasons. These observations confirmed that the structure is remarkably stable, persisting for decades, without significant change in size or shape. The hexagon rotates with Saturn's interior, completing one rotation every 10 hours and 39 minutes, the same period as Saturn's radio emissions. What makes the hexagon particularly mysterious is its depth. Initial observations suggested it might be a shallow atmospheric phenomenon confined to the cloud tops. But Cassini's infrared instruments revealed that the structure extends at least 300 kilometers deep into Saturn's atmosphere, possibly much deeper. This implies that the hexagon is not a surface feature, but a fundamental aspect of Saturn's atmospheric dynamics. The hexagon's dimensions add to its strangeness. Each of its 6 sides measures approximately 14,500 kilometers long, making them roughly 2,000 kilometers longer than Earth's diameter. The entire structure could contain nearly 4 Earths. Within the hexagon sits a massive vortex centered on Saturn's pole, with an eye approximately 50 times larger than the average hurricane eye on Earth. Multiple smaller vortices exist within the hexagon, some rotating clockwise, while the hexagon itself and the central vortex rotate counterclockwise. The winds at the hexagon's boundary reach velocities of approximately 320 kilometers per hour. The structure's color changed over the course of Cassini's mission, shifting from primarily blue tones to more golden hues as Saturn's northern hemisphere transitioned from winter to summer. Scientists have developed several hypotheses to explain the hexagon's formation. Laboratory experiments have demonstrated that rotating fluids can spontaneously generate polygonal patterns under specific conditions. When a circular container of fluid is rotated at different speeds at its center and edges, the boundary between these regions can form stable geometric shapes, including hexagons. The most detailed theoretical work suggests that the hexagon forms where Saturn's eastward jet stream interacts with smaller cyclones in the polar region. These smaller storms effectively pinch the jet stream, constraining its flow and causing it to develop a polygonal shape. Computer simulations incorporating deep thermal convection within Saturn's atmosphere have produced structures similar to the observed hexagon, though matching all the observed features remains challenging. What remains unexplained is why Saturn's hexagon maintains such precise geometric form. Atmospheric phenomena typically exhibit irregular boundaries and constantly shifting shapes. Storms drift, merge, and dissipate. Jet streams meander. The hexagon's sharp corners and straight edges, maintained over decades despite Saturn's turbulent atmospheric dynamics, represent something unusual in planetary meteorology. The hexagon also raises questions about Saturn's deep interior. If the structure extends thousands of kilometers into the atmosphere, as some models suggest, it implies coupling between Saturn's visible cloud layers and much deeper atmospheric regions. This coupling could reveal information about heat transport, internal rotation rates, and the planet's thermal structure. Recent observations by the James Webb Space Telescope detected unexpected features in Saturn's atmosphere above the hexagon, including dark, bead-like structures in the ionosphere that may relate to the hexagon's formation mechanisms. These structures remain unexplained and suggest that the hexagon's influence extends beyond the atmospheric layers where it is most visible. Saturn's south pole does not have a hexagon, though it does contain a vortex similar to the one found at the North Pole. This asymmetry adds another layer to the mystery. If hexagons formed naturally in rotating fluid systems under the right conditions, why does only Saturn's North Pole Exhibit 1. What differs between the two poles that allows the northern hexagon to form and persist, while the southern pole remains free of such structures? The hexagon's persistence over multiple decades, its geometric precision, and its coupling to deep atmospheric layers make it one of the most intriguing and least understood features in the solar system. It demonstrates that even relatively well-studied planets like Saturn can harbor phenomena that defy simple explanation. The universe continues to present structures that challenge intuition and require sophisticated physics to even begin comprehending. For now, the hexagon remains a mystery, not because scientists lack theories, but because fully testing those theories requires observations and measurements not yet available. Future missions may provide the data needed to definitively explain the hexagon's formation and maintenance. Until then, it stands as a reminder that the solar system contains many phenomena that resist easy understanding, even when viewed with the most advanced instruments humanity has built. Mars appears almost welcoming compared to Venus or Jupiter. Its surface temperature, while cold by Earth standards, remains within a range that specialized equipment can manage. Its atmosphere, though thin, does not crush or corrode. No extreme radiation belts threaten electronics. From a planetary science perspective, Mars is accessible. Yet Mars possesses its own forms of hostility, particularly in the planet-wide dust storms that occasionally engulf its entire surface. These storms represent weather phenomena of extraordinary scale and duration, far exceeding anything Earth experiences and presenting unique challenges for spacecraft and future human missions. Mars's atmosphere is thin, approximately 1% the density of Earth's atmosphere at sea level. This thinness might suggest that weather phenomena would be correspondingly mild. But Mars's low atmospheric pressure creates conditions where dust particles, once lifted into the air, can remain suspended for extended periods. The reduced gravitational pull on these particles allows even moderate winds to generate dust clouds. Local dust storms occur frequently on Mars. Regional dust storms, covering areas comparable to continents on Earth, develop several times each Martian year, but approximately once every 3 to 4 Earth years. Conditions align to produce planet-encircling dust storms that obscure the entire Martian surface for weeks or months. The 2018 global dust storm began in late May as a relatively modest local storm in Mars's southern hemisphere. Within weeks, it had expanded to cover the entire planet. The storm blocked so much sunlight that NASA's Opportunity rover, operating on solar power, went into hibernation mode as its batteries depleted. Opportunity never recovered from that hibernation. The rover, which had operated for nearly 15 years and traversed over 45 kilometers of Martian terrain, was finally silenced by dust blocking the sun. These global storms develop through a feedback process. Dust lifted into the atmosphere absorbs sunlight, heating the surrounding air. The heated air rises, creating winds that lift more dust. This process becomes self-reinforcing, and under the right conditions, the storm can expand to cover the entire planet. The dust remains suspended for weeks or months, gradually settling as the storm's energy dissipates. The thickness of the dust layer during these storms reduces surface illumination dramatically. During the 2018 event, some regions experienced conditions comparable to twilight at midday, with sunlight levels dropping to less than 1% of normal Martian conditions. This darkness is not merely inconvenient. For solar-powered systems, it represents a potentially fatal loss of power. The dust itself is not chemically hazardous, like Venus's sulfuric acid clouds. Martian dust consists primarily of iron oxide minerals, similar to rust, along with various silicates and other compounds common in planetary surfaces. The hazard comes not from toxicity, but from its fine particle size and static electrical properties. The particles carry electrostatic charges that cause them to cling to surfaces, infiltrate seals and mechanisms, and resist removal by simple brushing or shaking. For future human missions to Mars, these dust storms present significant operational challenges. Dust accumulation on solar panels reduces power generation. Dust infiltration into mechanical systems causes wear and potential failure. The reduced visibility makes navigation and outdoor activities hazardous. The storm's unpredictability means that mission planning must account for the possibility of prolonged periods with limited surface access and reduced power availability. Current Mars missions use various strategies to operate during dust storms. The Curiosity and Perseverance rovers employ radioisotope thermoelectric generators rather than solar panels, providing power independent of sunlight. Spacecraft in orbit can continue observations, though dust in the atmosphere affects image quality. Weather monitoring from multiple platforms provides early warning of developing storms, allowing time for precautionary measures. What makes Martian dust storms particularly noteworthy is their global scale and duration. Earth experiences large dust storms, particularly in regions like the Sahara Desert and the Gobi Desert, but these remain regional phenomena that dissipate within days or weeks. The idea of a storm covering an entire planet, persisting for months, and reducing sunlight to twilight levels has no terrestrial analogue. This difference reflects Mars's unique atmospheric conditions. The thin atmosphere means that once dust is suspended, it falls slowly. The lack of precipitation means no rain removes dust from the air. The planet's low gravity requires less energy to lift dust initially. These factors combine to create an environment where dust storms, once initiated, can grow to planet-wide scale and persist far longer than similar events on Earth. Understanding Martian dust storms requires continued observation over multiple Mars years. Each storm provides data on initiation conditions, growth patterns, and dissipation timescales. This accumulated knowledge will be essential for planning future missions, whether robotic or human, that must operate reliably despite occasional planetary-scale dust events. For now, Martian dust storms serve as a reminder that even planets more hospitable than Venus or Jupiter possess weather phenomena capable of overwhelming human technology. The storms are not violent in the sense of high winds or destructive forces, but they are pervasive, long-lasting, and capable of shutting down solar-powered systems for extended periods. In a survival situation, this could prove fatal. Neptune sits at the edge of the solar system, almost 30 times farther from the Sun than Earth. It receives less than 1% of the solar energy that reaches Earth. Yet Neptune possesses some of the most violent weather in the solar system, with wind speeds that exceed any other planet's atmospheric velocities. And beneath those supersonic winds, in the planet's deep interior, models of Neptune's interior structure suggest that, at depths of approximately 8,000 kilometers below the cloud tops, pressures reach millions of times. Earth's atmospheric pressure and temperatures climb to several thousand degrees Kelvin. Under these conditions, methane molecules present in Neptune's atmosphere are thought to decompose and reform as diamond crystals. This process, sometimes called diamond rain, remains theoretical rather than directly observed. No spacecraft has probed Neptune's deep interior, and current technology cannot survive the conditions necessary to reach those depths. But the physics is straightforward. Methane consists of one carbon atom bonded to 4 hydrogen atoms. Under extreme pressure and temperature, those bonds break. The carbon atoms, under continued pressure, arrange themselves into diamond's crystalline structure. Laboratory experiments have demonstrated that similar conditions can indeed produce diamond formation from methane under pressure. Researchers have subjected methane to shock-wave compressions, approximating Neptune's interior conditions, and observed diamond crystal formation. These experiments provide empirical support for the diamond rain hypothesis, though they cannot prove that the process occurs naturally within Neptune. If diamond rain does fall in Neptune's interior, the crystals would not remain suspended. Diamond is denser than the surrounding fluid, so the crystals would sink toward Neptune's core. Over billions of years, this process might have accumulated substantial quantities of diamond in Neptune's deep interior, creating layers of crystallized carbon surrounding the planet's rocky core. The scale of this hypothetical phenomenon staggers comprehension. Neptune contains vastly more methane than Earth's entire atmosphere. If even a small fraction of that methane has decomposed into diamond over the planet's 4.6 billion year history, the accumulated mass of diamond could measure in billions of tons. This would make Neptune's interior a repository of crystallized carbon on a scale that has no terrestrial analogue. Uranus likely experiences similar conditions. The two planets share comparable sizes, compositions, and interior structures. Models of Uranus's interior suggest similar pressure and temperature profiles, implying that diamond formation may occur there as well. The ice giants, as Neptune and Uranus are classified, may both contain substantial diamond layers in their deep interiors. This possibility adds another layer to Neptune's exotic character. Not only does the planet possess the most violent winds in the solar system, driven by internal heat rather than solar energy, but its interior may host processes that transform atmospheric gases into precious gemstones on scales unimaginable on Earth. The broader implication extends beyond Neptune itself. Throughout the universe, gas giants and ice giants orbit other stars. Many of these exoplanets possess compositions and interior conditions similar to Neptune and Uranus. The processes occurring in Neptune's interior likely operate in countless other planetary systems, making diamond formation in planetary interiors a widespread phenomenon rather than a unique oddity. Voyager 2, during its 1989 flyby of Neptune, measured wind speeds of approximately 1,200 miles per hour near the planet's equator. These winds move in a direction opposite to Neptune's rotation, creating a supersonic jet stream flowing westward relative to the planet's surface. The energy required to drive such winds comes not from solar heating, which is minimal at Neptune's distance, but from the planet's internal heat. Neptune radiates approximately 2.6 times more energy into space than it receives from the Sun. This internal heat source drives convection in the planet's atmosphere, creating temperature differences that power winds. The mechanism is similar to how Earth's interior heat drives plate tectonics and volcanic activity, but in Neptune's case, the energy manifests as atmospheric motion rather than geological activity. The combination of internal heating and the planet's rapid rotation, approximately 16 hours per day, creates conditions favorable for extreme winds. The rotation generates Coriolis forces that organize atmospheric motion into structured jet streams and storm systems. The internal heat provides continuous energy input, preventing the atmosphere from settling into calm equilibrium. Neptune's winds exist in an atmosphere composed primarily of hydrogen and helium, with traces of methane that give the planet its blue color. The temperatures at Neptune's cloud tops range from approximately -218 degrees Celsius to -200 degrees Celsius. In this cold environment, methane exists as ice crystals, forming clouds that interact with the powerful wind systems. The wind speeds themselves challenge engineering limits for spacecraft. If a probe were to descend into Neptune's atmosphere, it would need to withstand not just the increasing pressure and temperature of deeper atmospheric layers, but also wind forces capable of tearing apart structures not specifically designed for such conditions. The mechanical stress from 1,200 mile-per-hour winds would require extraordinary structural reinforcement. What makes Neptune's winds particularly mysterious is their energy source. The Sun's heating, which drives most atmospheric dynamics on Earth and the inner planets, contributes negligibly to Neptune's atmospheric energy budget. The internal heat source, likely residual heat from the planet's formation billions of years ago, combined with possible slow gravitational contraction, has maintained Neptune's violent atmospheric dynamics across geological timescales. Uranus, the seventh planet from the Sun, possesses one of the strangest characteristics of any planet in the solar system. Its axis of rotation is tilted 98 degrees relative to its orbital plane. This means that Uranus essentially rotates on its side, with its poles pointing toward locations on its orbital path, where other planets have their equators oriented toward the Sun. The consequence of this extreme tilt is that Uranus experiences seasons unlike those on any other planet. Each pole faces the Sun continuously for approximately 42 Earth years during Uranian summer, then faces away from the Sun for 42 Earth years during Uranian winter. The equatorial regions experience more familiar day-night cycles, but even these regions undergo dramatic seasonal variations as the Sun's path across the sky changes dramatically throughout Uranus's 84-year orbit around the Sun. This unusual rotation almost certainly results from a massive collision early in the solar system's history. Models suggest that Uranus was struck by an object, perhaps twice Earth's mass, during the period of planetary formation, when large impacts were common. The collision transferred enough angular momentum to knock Uranus onto its side, fundamentally altering the planet's rotational axis. This impact would have been catastrophic by any standard. The collision energy would have been sufficient to melt much of Uranus's interior, possibly ejecting substantial amounts of material into space. Some of that ejected material may have coalesced to form Uranus's moons, which orbit in the same highly inclined plane as the planet's equator, suggesting they formed from debris scattered by the collision. Evidence for this collision scenario comes from computer simulations of planetary formation and from Uranus's current characteristics. The planet's magnetic field is significantly offset from its center and tilted relative to its rotation axis, suggesting a disrupted interior structure, possibly resulting from incomplete settling after a major impact. Uranus also radiates very little excess heat compared to Neptune, despite the two planets having similar sizes and compositions, possibly because the collision disrupted Uranus's internal heat transport. The collision would have occurred billions of years ago, during the first few 100 million years after the solar system's formation, when planetary embryos migrated through the solar system and collisions between large bodies were relatively common. The same period likely saw the impact that formed Earth's moon, the impact that stripped Mercury of much of its rocky mantle, and numerous other catastrophic collisions that shaped the final arrangement of the solar system. Uranus's orientation creates unusual atmospheric dynamics. During the planet's long polar days, one hemisphere receives continuous sunlight for decades, while the other hemisphere experiences continuous darkness. This should create extreme temperature differences between the illuminated and dark hemispheres, driving powerful atmospheric circulation. Yet observations show that Uranus's atmosphere remains relatively calm compared to Neptune's, despite Neptune receiving less solar energy. This calmness may relate to Uranus's low internal heat output. Neptune's powerful winds are driven primarily by internal heat rather than solar heating. Uranus, radiating less internal heat, lacks this strong internal energy source. The result is an atmosphere that, while still dynamic, with winds reaching several hundred miles per hour, remains less violent than Neptune's, despite the extreme seasonal forcing from the tilted rotation axis. Voyager 2, the only spacecraft to visit Uranus, flew past the planet in 1986 during southern summer, when Uranus's south pole pointed nearly directly at the Sun. The spacecraft observed a relatively bland atmosphere with few visible cloud features, leading to initial impressions of Uranus as a quiet world. Later observations from the Hubble Space Telescope and ground-based observatories during other seasons revealed more atmospheric activity, including storm systems and cloud bands that develop as different regions of the planet rotate through changing solar illumination. Uranus's ring system, discovered in 1977 through stellar occultations, consists of narrow, dark rings, quite different from Saturn's bright, broad rings. These rings may also have formed from the collision that tilted Uranus, representing remnant material that failed to accrete into moons. The rings' darkness suggests they consist of material rich in organic compounds or radiation-processed ices, giving them a charcoal-like appearance. The planet's magnetic field adds another layer of strangeness. Unlike Earth's magnetic field, which is roughly aligned with the planet's rotation axis, Uranus's magnetic field is tilted approximately 59 degrees from the rotation axis and offset from the planet's center by about 1/3 of the planet's radius. This creates an asymmetric magnetosphere that wobbles as the planet rotates, generating unusual charged particle dynamics and auroral behavior. When Uranus's magnetic field was discovered during Voyager 2's flyby, scientists initially suggested this configuration might represent a planetary magnetic field caught in the process of reversing polarity, similar to Earth's magnetic reversals that occur every few 100,000 years on average. But Neptune's magnetic field, measured 3 years later during Voyager 2's Neptune encounter, showed a similar offset and tilt, suggesting that ice giant magnetic fields naturally adopt this configuration due to the planet's internal structures. The collision that tilted Uranus represents one of many violent events during the solar system's formation, a reminder that the orderly planetary arrangement visible today emerged from an era of chaos and catastrophic impacts. Understanding Uranus's unusual characteristics requires accepting that the planet underwent an experience so extreme that it permanently altered its fundamental properties, changing its rotation, possibly affecting its internal structure, and creating a world unlike any other in the solar system. The supersonic nature of Neptune's winds creates additional complexity. When gas flows faster than the speed of sound in that medium, shock waves form. These shock waves represent discontinuities in pressure, temperature, and density, creating regions where atmospheric conditions change abruptly. The interaction of supersonic winds with Neptune's storm systems and cloud formations generates dynamics more complex than those found in subsonic atmospheric flows. Observations from Earth-based telescopes and the Hubble Space Telescope have documented changes in Neptune's atmospheric features over years and decades. Large storm systems, including dark spots comparable in some ways to Jupiter's Great Red Spot, appear and dissipate on timescales of months to years. These observations confirm that Neptune's atmosphere remains actively dynamic, despite its distance from the Sun and its cold temperatures. Neptune's moon Triton presents additional mysteries related to Neptune's atmospheric dynamics. Triton possesses its own tenuous atmosphere and exhibits geysers of nitrogen gas erupting from its surface. The gravitational interaction between Neptune and Triton generates tidal heating that provides energy for these geological processes, demonstrating that extreme conditions extend beyond Neptune itself to affect its satellite system. The implications for future exploration are sobering. Neptune remains one of the least explored planets in the solar system, visited only once by Voyager 2 inches, a brief flyby. Future missions would need to account for wind forces unprecedented elsewhere in the solar system, atmospheric dynamics driven by internal rather than external heating, and the challenge of operating at distances where sunlight provides negligible power. Neptune's winds serve as a reminder that extreme conditions exist even in the coldest, most distant regions of the solar system. The violence is not hot violence like Venus's crushing heat or Jupiter's radiation. It is cold violence, winds powerful enough to strip material from surfaces, driven by heat escaping from a planet's interior, operating in near total darkness at the edge of interplanetary space. Mercury orbits closer to the Sun than any other planet, completing each orbit in just 88 Earth days. Its proximity to the Sun might suggest uniform high temperatures, but Mercury's environment is characterized not by consistency, but by extremes. The planet experiences temperature swings more dramatic than any other world in the solar system, with surface conditions varying by more than 1,000 degrees Fahrenheit between day and night. During Mercury's long daytime, which lasts approximately 59 Earth days due to the planet's slow rotation, surface temperatures in sunlit regions climb to approximately 800 degrees Fahrenheit, hot enough to melt lead and zinc. The Sun appears more than twice as large in Mercury's sky as it does from Earth, delivering solar radiation approximately 7 times more intense than Earth receives. But Mercury possesses almost no atmosphere to retain or redistribute this heat. The planet's atmospheric pressure measures less than 1/1,000,000th of Earth's atmospheric pressure at sea level. This is effectively a vacuum from a practical standpoint, providing no insulation and no mechanism for heat transfer from day side to night side. As a result, when regions of Mercury rotate into nighttime, temperatures plummet catastrophically. Surface temperatures on the night side drop to approximately minus 290 degrees Fahrenheit. This represents one of the coldest surface temperatures measured on any inner solar system body, colder than many locations on Mars, despite Mercury's proximity to the Sun. The temperature differential between Mercury's day and night sides exceeds 1,000 degrees Fahrenheit, creating thermal stress that would shatter most materials. Rocks expand when heated and contract when cooled. On Mercury, this cycle repeats with each rotation, subjecting surface materials to continuous mechanical stress across temperature ranges far beyond what Earth's geology experiences. Mercury's day-night temperature extremes result from the combination of its proximity to the Sun, its lack of atmosphere, and its unusual rotation pattern. The planet is tidally locked to the Sun in a 3-to-2 resonance, meaning it rotates 3 times for every 2 orbits around the Sun. This creates a situation where some surface locations experience longer exposure to direct sunlight than others, depending on their position relative to Mercury's eccentric orbit. Near Mercury's equator, at 2 specific locations called the subsolar points, where the Sun passes directly overhead at perihelion, surface temperatures can exceed 800 degrees Fahrenheit. These are the hottest surface locations in the solar system outside of Venus. The combination of Mercury's elliptical orbit and its 3-to-2 rotation resonance creates these temperature hotspots that experience even more intense solar heating than Mercury's average dayside temperatures. Yet despite these extreme surface temperatures, Mercury possesses water ice. NASA's Messenger spacecraft, which orbited Mercury from 2011 to 2015, detected evidence of water ice deposits in permanently shadowed craters near Mercury's poles. These craters never received direct sunlight, maintaining temperatures cold enough for water ice to remain stable despite the planet's proximity to the Sun. The existence of water ice on Mercury demonstrates how extreme the planet's temperature variations can be. Within a few hundred kilometers, surface temperatures range from 800 degrees Fahrenheit in sunlit regions to cold enough for permanent water ice in shadowed craters. No other planet in the solar system exhibits such dramatic temperature gradients over such short distances. For future spacecraft missions, Mercury's temperature extremes present significant engineering challenges. Electronics must function across a temperature range that spans more than 1,000 degrees Fahrenheit. Structural materials must withstand repeated thermal cycling. Power systems must handle both the intense solar radiation available on the day side and the extreme cold of the night side. Messenger demonstrated that these challenges can be overcome. The spacecraft employed a large sun shield to protect sensitive components from direct solar radiation, used heat-resistant materials throughout its structure, and carefully managed its orbit to avoid prolonged exposure to Mercury's most extreme thermal environments. Even with these precautions, The spacecraft's operational lifetime was limited by the accumulation of thermal stress on its systems. Mercury's surface environment combines the temperature extremes with other hazards. The lack of atmosphere means that micrometeorites, which would burn up in Earth's atmosphere, strike Mercury's surface directly at velocities of tens of kilometers per second. These impacts gradually pulverize surface materials, creating a layer of fine dust called regolith that covers the planet's bedrock. Solar wind particles also strike Mercury's surface directly without atmospheric filtering. These high-energy particles interact with surface materials, creating a thin exosphere of atoms knocked loose from the regolith. This exosphere is so tenuous that it meets the definition of a vacuum, yet it can be detected and studied by sensitive instruments, providing information about Mercury's surface composition. Mercury's proximity to the Sun also subjects the planet to intense bursts of solar radiation during solar flares. The planet has no atmosphere to absorb or scatter this radiation, meaning that surface radiation levels can spike dramatically during solar events. Any future human mission to Mercury would need to account for this radiation hazard. In addition to the temperature extremes, the planet's small size and high density indicate that Mercury possesses a disproportionately large metallic core, occupying approximately 85% of the planet's radius. This unusual internal structure may result from a massive impact early in Mercury's history that stripped away much of the planet's original rocky mantle, leaving behind a world dominated by its iron-rich core. Mercury's magnetic field, though weaker than Earth's, provides evidence of this large metallic core. The field is strong enough to create a small magnetosphere that partially deflects solar wind particles. This magnetosphere, while modest by Earth standards, represents one of the few protective features Mercury possesses against the space environment. Understanding Mercury requires accepting that proximity to the Sun does not guarantee warmth. Without an atmosphere to trap and redistribute heat, Mercury experiences temperature extremes that would be impossible on worlds with substantial atmospheres. The planet serves as a reminder that habitability depends not just on distance from the Sun, but on atmospheric properties that Earth possesses and Mercury lacks. The Sun makes life on Earth possible. Its energy drives photosynthesis, creates weather patterns, and maintains temperatures within the range necessary for liquid water. From Earth's surface, the Sun appears calm and steady, rising and setting with predictable rhythm, providing light and warmth with comfortable reliability. Yet the Sun is a star, powered by nuclear fusion occurring in its core, and it occasionally releases energy in sudden, violent bursts, capable of affecting the entire solar system. These solar flares and coronal mass ejections represent normal stellar behavior, but from a human technological perspective, they pose significant hazards. Solar flares occur when magnetic energy stored in the Sun's atmosphere is suddenly released. This energy heats plasma to tens of millions of degrees and accelerates charged particles to relativistic velocities. The resulting emissions span the electromagnetic spectrum, from radio waves through visible light to X-rays and gamma rays. Large solar flares release energy equivalent to billions of nuclear weapons detonating simultaneously. Coronal mass ejections are even more energetic events, where the Sun ejects vast quantities of plasma and magnetic field into space. A large coronal mass ejection can release more than 1 billion tons of material, traveling at speeds up to several million miles per hour. When directed toward Earth, these ejections can interact with Earth's magnetic field and atmosphere, creating geomagnetic storms. The Carrington event of 1859 represents the most powerful geomagnetic storm in recorded history. Telegraph systems across Europe and North America experienced disruptions. Some telegraph operators reported receiving electric shocks from their equipment. Telegraph lines sparked, in some cases setting telegraph paper on fire. Aurora displays were visible as far south as the Caribbean and Hawaii, regions where auroras are normally never seen. If a solar storm of Carrington event magnitude occurred today, the consequences would be far more severe. Modern civilization depends on electrical grids, satellite communications, GPS navigation, and countless electronic systems vulnerable to geomagnetic disruption. A sufficiently powerful geomagnetic storm could induce currents in long electrical conductors, potentially damaging transformers and causing widespread power outages lasting weeks or months. Satellite systems face particular vulnerability. Satellites in low Earth orbit experience increased atmospheric drag during geomagnetic storms as the upper atmosphere heats and expands. This can cause satellites to lose altitude more rapidly than anticipated, potentially leading to loss of control or premature re-entry. High-energy particles can damage solar panels, degrade electronic components, and disrupt onboard computer systems. The Sun's activity follows an approximately 11-year cycle, with solar maximum periods characterized by increased numbers of sunspots, more frequent solar flares, and higher probability of coronal mass ejections. During solar minimum, these events become less frequent, but do not cease entirely. Large solar eruptions can occur at any point in the solar cycle. Space weather forecasting has improved significantly in recent decades. NASA's Solar Dynamics Observatory continuously monitors the Sun, providing real-time data on solar activity. The Advanced Composition Explorer spacecraft, positioned between Earth and the Sun, can provide approximately 15 to 60 minutes advance warning of arriving solar wind disturbances. This warning time allows some protective measures, but is insufficient for comprehensive responses to major events. The Sun's energy output varies by less than 0.1% over the solar cycle. This small variation has minimal effect on Earth's climate compared to other factors, but it demonstrates that the Sun is not a perfectly constant energy source. The Sun's magnetic field reverses polarity every 11 years, with the north and south magnetic poles exchanging positions. This reversal process connects to the mechanisms driving solar flares and coronal mass ejections. Understanding solar activity requires monitoring across multiple wavelengths. The Sun appears different when observed in visible light, ultraviolet, X-rays, or radio waves. Each wavelength reveals different layers of the solar atmosphere and different physical processes. Coordinated observations from multiple spacecraft and ground-based observatories provide complementary views necessary for comprehensive understanding. The threat of catastrophic solar storms has prompted discussions of protective measures. Electrical grid operators can take precautions when advance warning of geomagnetic storms is received, such as reducing power loads and disconnecting certain transformers. Satellite operators can place sensitive spacecraft in safe modes during high-risk periods. Aviation authorities can reroute flights to avoid polar regions where radiation exposure increases during solar events. But these measures remain reactive rather than preventive. The Sun will continue producing flares and coronal mass ejections regardless of human preparations. The only question is when the next major event will occur and whether it will be directed toward Earth. Statistically, events comparable to the Carrington storm occur approximately once per century. Smaller, but still significant events occur more frequently. The Sun's violence is not a malfunction or an anomaly. It represents normal stellar behavior driven by magnetic field dynamics in the solar atmosphere. These same processes occur on other stars throughout the universe. What makes the Sun's activity relevant to humanity is simply proximity. We orbit a star, and stars occasionally release enormous amounts of energy in short timescales. From a cosmic perspective, the Sun is a remarkably stable star. Its energy output varies far less than many other stars. Its flares and eruptions, while dramatic by human standards, are modest compared to the most active stars. Humanity exists in the solar system during a relatively calm epoch of solar evolution, but calm is relative. The Sun remains capable of disrupting technological civilization through electromagnetic pulses and geomagnetic disturbances. This capability represents a permanent feature of our relationship with the star that sustains us. The solar system extends far beyond the familiar planets. In the outer regions, beyond Neptune's orbit, lies a vast collection of icy objects known as the Kuiper Belt. Here, thousands of small worlds orbit in near darkness, frozen remnants from the solar system's formation 4.6 billion years ago. Among these objects are some with sufficient mass to be considered dwarf planets. Pluto, the most famous Kuiper Belt object, orbits between 30 and 50 astronomical units from the Sun, where temperatures plunge below -230 degrees Celsius. At these distances, the Sun appears merely as a bright star, providing negligible heat and light. The Kuiper Belt contains not only small icy bodies, but also objects with masses comparable to Pluto. These worlds follow elliptical orbits that occasionally bring them closer to the Sun, where solar heating causes surface ices to sublimate, creating temporary atmospheres and, in some cases, comet-like activity. The belt's population includes objects with varied compositions, including water ice, methane ice, ammonia ice, and rocky material. What makes the Kuiper Belt particularly intriguing and vaguely unsettling is what it might contain that remains undiscovered. The region's vast size and the faintness of its objects mean that comprehensive surveys remain incomplete. Mathematical models suggest that numerous large objects await discovery, potentially including worlds as large as, or larger than Pluto, that have escaped detection due to their extreme distance or unfavorable orbital positions. The existence of the Oort cloud, a theoretical sphere of icy objects surrounding the solar system at distances up to 100,000 astronomical units, adds another dimension to this picture. The Oort cloud has never been directly observed. Its existence is inferred from the orbits of long-period comets, which arrive from all directions with orbital periods measured in thousands or millions of years. These comets must originate somewhere, and the Oort cloud provides the most plausible source. If the Oort cloud exists as theorized, it contains trillions of objects ranging from house-sized chunks to bodies potentially as large as small planets. These objects remain in deep freeze, their surfaces never warmed above a few degrees above absolute zero. They orbit so far from the Sun that perturbations from passing stars can alter their trajectories, occasionally sending objects falling inward toward the inner solar system. This creates a scenario where objects from the outer reaches of the solar system could, given the right gravitational disturbance, begin falling toward Earth's neighborhood after traveling for thousands or millions of years. The timescales involved mean that such events are rare, but the impact hazard from long-period comets represents a real, if low probability, risk. The asteroid belt between Mars and Jupiter presents a more immediate and better characterized population of potential impactors. This belt contains hundreds of thousands of rocky objects, ranging from dust-sized particles to Ceres, a dwarf planet nearly 1,000 kilometers in diameter. Most asteroids remain in stable orbits that pose no threat to Earth, but gravitational interactions occasionally perturb objects into orbits that cross Earth's path. NASA's Near-Earth Object Observations Program has identified tens of thousands of near-Earth asteroids, tracking their orbits and assessing impact risk. The program has determined that no large asteroid poses a significant threat of Earth impact in the foreseeable future, but the catalogue remains incomplete for smaller objects, and the possibility of discovering a previously unknown asteroid on a collision course exists. The Chelyabinsk meteor of 2013 provided a reminder of this hazard. An asteroid approximately 20 meters in diameter entered Earth's atmosphere over Russia, exploding at an altitude of about 30 kilometers, with an energy equivalent to approximately 500 kilotons of TNT. The resulting airburst damaged buildings over a wide area and injured more than 1,000 people. primarily from broken glass. This impactor was small by astronomical standards and arrived with no warning. Larger objects can be detected years in advance, providing time for potential deflection missions. But the Chelyabinsk event demonstrated that even relatively small asteroids can cause significant damage if they strike populated areas. The distinction between asteroids and comets blurs in the outer solar system. Some objects classified as asteroids may be dormant comets, with most of their volatile material already lost. Some objects appear asteroid-like when far from the Sun, but develop comet-like activity when solar heating increases. The taxonomy of small bodies continues to evolve as observations reveal more complexity. What remains clear is that the solar system contains vast numbers of small objects whose orbits are not perfectly stable over geological timescales. Most pose no threat to Earth, but the population is large enough that occasional impacts remain statistically inevitable. The only questions are when the next significant impact will occur, how large the impactor will be, and whether advanced detection will provide time for protective measures. Surveillance programs have significantly improved humanity's ability to detect and track potential impactors. Ground-based telescopes scan the sky systematically, looking for moving objects against the stellar background. Space-based observatories provide complementary views, free from atmospheric distortion and daylight limitations. Mathematical models predict future positions with high accuracy, allowing risk assessment decades in advance. But detection is not prevention. If a hazardous object were discovered on a collision course with Earth, deflection would require years of lead time and technologies that have never been tested under real conditions. The recent DART mission successfully demonstrated that spacecraft impacts can alter an asteroid's trajectory. But practical deflection of a large asteroid would require much more extensive intervention. The solar system's population of small bodies represents both a scientific resource and a potential hazard. These objects preserve records of the solar system's formation and early evolution. They contain materials that may have delivered water and organic compounds to early Earth. They represent potential resources for future space exploration, but they also represent the constant background threat of cosmic impact that has shaped planetary evolution throughout solar system history. The solar system's structure extends far beyond the visible planets and moons. Gravity organizes matter into predictable patterns, but within those patterns, chaos operates on multiple timescales. Objects perturbed from stable orbits begin long journeys that may eventually intersect with Earth. The timescales are geological, but the consequences, when they arrive, are immediate. The sun will not shine forever. Stars are born, live out their active lives, and eventually die, following paths determined by their initial mass. The sun, a medium-sized star, will eventually evolve into a red giant, expanding until its outer layers engulf the inner planets, including Earth. This future lies approximately 5 billion years away. Current observations and stellar evolution models provide clear predictions of how this process will unfold. As the sun exhausts the hydrogen fuel in its core, fusion will begin in a shell around the core, causing the star's outer layers to expand dramatically. The sun's luminosity will increase, its surface temperature will decrease, and its radius will extend to perhaps 200 times its current size. Mercury will certainly be consumed by the expanding sun. Venus likely will be as well. Earth's fate remains less certain in the models. The sun will lose mass as its outer layers expand, weakening its gravitational pull on the planets. Earth's orbit may expand outward as a result, potentially carrying it beyond the sun's eventual maximum radius. But even if Earth technically survives engulfment, it will not survive as a habitable world. Long before the sun expands into a red giant, its gradually increasing luminosity will make Earth uninhabitable. The sun's energy output increases by approximately 10% every billion years, as hydrogen fusion reactions in its core gradually intensify. Within a billion years, this increased luminosity will warm Earth enough to accelerate water evaporation, increasing atmospheric water vapor and strengthening the greenhouse effect. This creates a runaway process. Warmer temperatures lead to more evaporation. More water vapor in the atmosphere strengthens the greenhouse effect, which raises temperatures further, leading to more evaporation. Eventually, Earth's oceans will evaporate entirely. The planet will become a scorched desert world with surface temperatures capable of melting lead, similar to present-day Venus. The timescale provides some comfort. 1 billion years represents an immense duration, far longer than complex life has existed on Earth. But it also represents a definite endpoint. Earth's habitability has a fixed expiration date determined by the Sun's evolution. Life on Earth, if it persists, must eventually either adapt to radically different conditions or migrate elsewhere. The Sun's death as a red giant will not be permanent. After exhausting the hydrogen fuel in its core and the shell surrounding the core, the Sun will eject its outer layers into space, forming a planetary nebula. The remaining core will contract into a white dwarf, a dense stellar remnant, approximately the size of Earth, but containing roughly half the Sun's current mass. White dwarfs produce no energy through fusion. They shine only by radiating away stored thermal energy, gradually cooling over trillions of years. The Sun's white dwarf remnant will eventually cool until it becomes a black dwarf, a theoretical endpoint of stellar evolution that no star has yet reached because the universe is not old enough. This distant future seems abstract and disconnected from present concerns, but it represents the ultimate fate of the star that makes human existence possible. The Sun is not eternal. Its energy output will not remain constant indefinitely. The stability that has allowed life to develop and flourish on Earth is temporary, a fortunate epoch between the violent conditions of the solar system's formation and the inevitable changes accompanying the Sun's eventual death. Understanding stellar evolution removes some mystery from the Sun's future. The processes are well understood through observations of other stars at different evolutionary stages. The timescales are predictable through stellar models validated by astronomical observations. But knowing the mechanism does not alter the outcome. The Sun will evolve, Earth will become uninhabitable, and the solar system as it currently exists will be radically transformed. Humanity has existed for perhaps 300,000 years. Complex life has existed on Earth for approximately 600 million years. The Sun has been shining in its current form for about 4.6 billion years, and will continue for another 5 billion years, before beginning its red giant phase. These timescales dwarf human experience, making the Sun's eventual death feel remote and abstract. Yet the certainty of that future adds a poignant dimension to Earth's history. Every organism that has ever lived, every evolutionary innovation, every mass extinction and recovery has occurred during a limited window of stellar stability that will eventually close. The biosphere, having adapted to a remarkably constant energy input from the Sun across hundreds of millions of years, will face conditions for which no adaptation is possible. For now, the Sun remains in the stable middle age of its life cycle. Its energy output varies by less than 0.1% over the 11-year solar cycle. Its surface temperature stays nearly constant. The nuclear reactions in its core proceed at a steady rate, converting mass into energy, according to Einstein's equation. This stability has persisted throughout human history and will continue for time periods far longer than civilization's duration. But that stability is not infinite. Stars change. The Sun is changing, slowly but inexorably, approaching a future where its current character will be lost. The solar system will persist, but it will be a fundamentally different place, with different conditions, different possibilities, and different constraints. Understanding this does not require action. The timescales remove any urgency, but it does provide perspective. The solar system, which seems so permanent and structured, is actually a dynamic system evolving toward eventual radical transformation. The stability experienced over human timescales represents a snapshot of a much longer process that began with the solar system's formation and will end with the Sun's transformation into a white dwarf billions of years from now. The journey through the solar system's disturbing realities reveals a consistent theme. Violence exists, but it is structured violence, operating according to consistent physical principles. Temperatures that melt lead on Venus result from well-understood greenhouse effects. Radiation belts that would kill humans in hours at Jupiter follow from electromagnetic theory and particle acceleration. Supersonic winds on Neptune derive from internal heat and rotational dynamics. These extreme conditions are not random or capricious. They represent the normal operation of physical processes at scales and intensities different from those encountered in everyday human experience. The solar system is not gentle, but it is lawful. The forces that create hostile environments operate predictably, allowing those environments to be studied, understood, and in some cases, navigated despite their dangers. Spacecraft have survived Venus's crushing heat long enough to transmit data. Probes have crossed Jupiter's radiation belts and continued functioning. Rovers have operated on Mars through planet-wide dust storms. Humanity has sent instruments to study every planet in the solar system, gathering data from environments no human could survive unprotected. This exploration required engineering that anticipated extreme conditions. Materials that withstand high temperatures and pressures. Electronics hardened against radiation. Power systems independent of sunlight. Communication systems capable of transmitting across billions of kilometers. Each successful mission represented careful planning, robust design, and acceptance of the risks inherent in exploring hostile environments. The disturbing facts about the solar system serve multiple purposes. They reveal the diversity of planetary environments. They demonstrate the range of conditions that physical processes can generate. They highlight the challenges facing future space exploration. And they provide context for Earth's remarkable habitability. Earth's surface temperature stays within a range that allows liquid water. Earth's atmosphere provides breathable air at comfortable pressure. Earth's magnetic field shields the surface from most harmful radiation. Earth's weather, while sometimes violent by human standards, remains modest compared to planet-wide dust storms or supersonic jet streams. These conditions are not guaranteed. They result from Earth's specific combination of size, composition, orbital position. The nearest planet sunward, Venus, became a furnace. The nearest planet outward, Mars, became a frozen desert. Earth occupies a position and possesses characteristics that allowed it to maintain conditions suitable for life across billions of years. That suitability is not universal or inevitable. It is specific, contingent, and ultimately temporary. Understanding the solar system's hostile environments does not diminish their danger, but does frame that danger appropriately. These are not supernatural threats or malicious forces. They are natural consequences of how matter and energy behave. The violence is real, but it is comprehensible violence, subject to physical law and therefore amenable to scientific investigation. As the night progresses and sleep beckons, these facts need not create anxiety. The solar system's structure has persisted for billions of years. The planets orbit as they have always orbited. The sun shines as it has always shined. The extreme conditions on other worlds do not threaten Earth's stability. They simply exist, distant and documented, part of the complex system humanity inhabits. There is an odd comfort in cosmic horror, properly understood. The vastness of space, the extremity of conditions on other worlds, the certainty of the sun's eventual death, all emphasize both Earth's uniqueness and the stability of physical law. The universe operates according to rules that apply everywhere, from Venus's furnace surface to Neptune's supersonic winds. Those rules create hostile environments, but they also make those environments predictable. Human existence occurs within a remarkably narrow band of conditions. Too much heat, too much cold, too much radiation, too much pressure. Any of these would be immediately fatal. Yet within Earth's protective bubble, conditions remain favorable, maintained by complex interactions between atmosphere, oceans, geological activity, and the sun's energy input. The solar system's disturbing facts provide perspective on this situation. Earth is not typical. Most environments in the solar system would kill humans within minutes or hours. The conditions that make Earth habitable are specific, limited, and maintained by ongoing processes. Understanding this does not require fear, but does suggest appropriate appreciation for the unusual circumstances that permit human existence. As this exploration draws toward rest, the solar system's violence becomes less personal and more abstract. These are facts about distant worlds, extreme conditions that exist beyond Earth's protective environment, documented by robotic explorers that venture where humans cannot survive. The knowledge is real. The dangers are real, but they remain at a comfortable distance, separated from Earth by millions of miles of empty space. Sleep can come with the understanding that the solar system, for all its hostility, continues operating according to knowable principles. The extremes exist, but they exist predictably. The violence operates, but it operates lawfully. And Earth, improbable and temporary, though its habitability may be, maintains the conditions necessary for rest, for dreams, and for the continuation of life that has flourished here across hundreds of millions of years. The universe does not require human comprehension to function. It proceeds regardless, following physical principles that govern everything, from quantum particles to galaxy clusters. The solar system is a small part of that vast structure, operating according to the same fundamental rules. Understanding some of those rules, seeing how they create both habitable worlds and deadly environments, adds depth to the picture, but does not change the reality. Better sleep, a lighter day.